maybe I can start. Okay. So last time I discussed about certain index, and then I made a mistake in computation. So therefore, I just do the correction of this. So last time I considered the mapping like this, so that f of tau 0 is always real, but f of tau 1 is lying in this like this. And then I compare it with other one. So g tau t, and this. Sorry, this is now g, and g tau 0 is always real, and g of tau 1 is also real. And then if I consider the operator like dd tau f plus square root minus 1 of dd t of f, what the corresponding operator here? So I made a mistake in computation. So in fact, this one corresponds to just d dt plus square root minus 1 of d dt plus maybe something like theta prime of tau t of g. And then finally I have this minus sign of this theta tau of g. So last time I saw that, yeah, in my note actually I had a plus sign, but on the blackboard actually I had a, no. In my note I have a minus sign, but on the blackboard I had a plus sign, so therefore I was a bit confused because my computation was somehow not correct. What I'm saying is just to write this one, and then maybe this one is just equal to this e to the sorry e, okay. So if I write this f tau t is equal to e to the square root minus 1 of theta tau t of g. So if I relate them by this, and then this one is actually correspond to something like this. So therefore I have here minus sign. And then just to try to understand the spectral flow, and then so if I consider operator like a d is equal to dd tau plus a tau, this is actually self-adjoint operator with, say, discrete spectrum. And then try to consider the index of this, and also assume that a of minus infinity and a plus infinity both invertible. And then index of this operator is equal to the number of eigenvalues lambda tau, lambda j tau, so that this lambda j tau becomes negative to infinity. So maybe I just write it. This one is negative, and lambda j plus infinity is positive. I actually assume very simple operator. So therefore, a tau of e of j is equal to lambda j tau of ej, and j is maybe in natural numbers, so that maybe integers, and yeah, this ej are complete orthonormal basis, right? So I consider such a very easy operator, and then this one is equal to this one minus number of eigenvalues, branchable eigenvalues, lambda j tau, so that this lambda j of minus infinity is positive, and lambda j plus infinity is negative. I think this is the right computation. Okay. I also assume that this A tau is constant operator. So A tau is equal to A plus minus infinity for tau sufficiently large. So I assume this. But anyway, so this somehow I said last time. And then if you look at the spectrum of this operator, it is actually spectrum this operator. But we know the spectrum of this operator very well. And because this one is actually compactly supported, so maybe for index actually we can drop this. We can actually drop this. And then the spectrum is something like, here I have maybe pi z. This is the spectrum of this operator. And then here I have this thing. Right? So if I have a function, so here I just write just the eigenvalue of this operator, like 0 and pi and 2 pi and minus pi and so on. And then just draw the function theta. So let's suppose that theta is something like suppose that theta is something like this. And then for this, actually, I mean this pi z minus theta. So I consider 2 pi minus theta. 2 pi minus theta is 0 here. But here, actually, 2 pi minus theta is negative. So corresponding to this eigenvalue, actually, the eigenvalue, the branch of this eigenvalue is negative here and positive here. So therefore, it contributes to this part. Right? So we have a such contribution for each intersection point. Right? So how many intersections with these pi z lines, yeah, with signs. So if you cross from in this way, and then it contributes plus, and if it is opposite way, it contributes negative. Okay? So somehow this computed, because last time I had this plus sign here, and then in the end I didn't really feel so comfortable because if you consider just some similar problem on the disk, and then if you consider the boundary condition, like so here it is here actually maybe it's e square root minus 1 theta, and then you just put that here theta, so theta r. So you consider some holomorphic map with boundary condition on the boundary. So at e of I consider some follow function f, so that if this one satisfies e to the square root minus 1 theta, wow, and can you have a solution for this or not? Certainly we have a solution because z itself has a solution, right? If it is actually 2 times theta, then you have z squared, the solution of this. So therefore, in fact, if this theta grows in this theta tau grows this way, and then the index must be positive in a sense. So that means in this picture, we have not a disk, but this infinite cylinder. And I fix boundary value here, and here I consider these things. Right? So therefore, somehow this theta must, if theta actually grows this way, and then the index must be positive. Right? So that is, now it's compatible, because if theta grows, theta getting bigger, and then some branch may become negative, although the value at plus infinity is negative. So therefore here the minus sign, so therefore the computation is actually okay. So maybe you can just take it one. So this is just a correction of the correction is just this. And then I now start discussing the obstruction classes, obstruction cycles. In Lagrangian Floer theory. So last time I discussed some examples, two-dimensional example. For instance, I have this torus, and then I have one meridian here, and then I have some small circle here, and then for this meridian may be L0, and longitude, this circle is L1, and then, so CF, L1, L0, certainly it's a module generated by two intersection points, and you may try to define some boundary operator like this, but this one is not zero, right? Because you have this holomorphic disk, and you have another holomorphic disk like this, and other holomorphic disk doesn't really contribute to this boundary operator. I mean, relative index must be 1, so therefore these are only 2. So therefore, if you apply red one and yellow one, and then somehow you come back to the same intersection point. And so maybe, no way to do this. I mean, in this case, no way. And now I consider another example that is a case of a two sphere, and then I have two circles like this, and then here I have P, and here I have Q here, and then I write the area here is A, and the area here is B, and the area here is C, and the area here is D. Then if I encode some information on the area, and then this may be delta P, maybe like a TA minus TC of Q, and delta Q is equal to I don't know, TB minus TD or P or something. And so in general, actually, again, delta square is non-zero, right? So generally, delta square is not equal to 0. But if these two are Hamiltonian isotopic, or maybe just related by area preserving diffeomorphism, then so if A equal to B, so A equal to C, say, so maybe I just write picture like this. I have a two circles like this. Maybe I just look at it from the above, then I can see this. And then here, maybe this is B. And here, maybe I have A, and I have C here. So if this circle is just moved to another circle by area preserving map, and then this area A is certainly equal to area of C, right? And then actually this one vanishes, so therefore certainly delta square is equal to 0. Right? But how this one is related to the discussion here? So last time what I said is somehow I have this thing, and then if I have this thing and this thing, right? So this is one of the boundary of certain modular space. Say, I don't know how to write it, but anyway, so maybe like this. Right? So this is the modular space, starting from P back to P. Right? You have a one-parameter family of holomorphic strips, and then parametered by the length of this. And so if this one, actually this segment tends to the diameter, and then you have this. And another side is this. And here, actually, the whole disk, the whole strip, actually degenerate to this. So here, actually, whole strip is mapped to here. But I have some disk bubble here, and then this disk bubble is mapped to here, right? So this is not the end correspond to this. So this is a different end. So therefore, even though you look at you understand the moduli space of dimension 1, yeah, there is another type of boundary. So therefore, this cannot be equal to 0. Yeah, delta square is not equal to 0. But in this case, certainly, you have the same thing, right? Because like a red one is from here to here, right? And we also have this one. Maybe a little bit strange. So, I don't know. So just distinguish them. Distinguish two circles. I just put some color here. So here is a green circle, and here is this blue circle. And I just want to say that these two red ones are actually satisfying the same boundary common boundary condition. Namely, if you start from this intersection point and then travel a little bit, and then the green one is on your right hand side and blue one is on your left hand side. Right? This one, the same thing. If you look at this starting from here, then you look at the right hand side, then you have a green one, and this red, blue one is your left hand side. So therefore, these two contribute to the boundary of these things. So if I start from P, then these two red ones contribute to the boundary of this, right? And then from Q, actually you have only one B, only one thing here. Certainly you have another one on the sphere correspond to D. But anyway, this is one of the picture. So in this case, you can look at this thing for this red yellow. So you have this red yellow. So you have this phenomena, and also you have this red yellow, right? So that one is somehow here. So here you have, I don't know which one should be, which one. Okay, so this one is actually blue one, and this one is green one, right? Green one. And then originally I consider the following thing. So here I have green one and blue one here. Okay? And then I want to consider this sort of holomorphic disk like this. Okay? So this sort of holomorphic disk. And then one boundary is certainly this, but the other boundary is the following. So the other boundary is somehow this and this, and here you have this, and then I have this green one. Sorry, I have this green one and blue one here, and everything here actually mapped to this intersection point, right? And this one is mapped to this one. Okay, so this is the contribution from this composition that's red and yellow, and we also have another one. So that is this one. Sorry, this one and this one, right? And now we consider a holomorphic disk like this. I think, yes, like this. think so. Like this. And then your holomorphic map is like this. Yes. Yes, yes, yes. Wait. Maybe a little bit strange or... Yeah. But then in the end, what we have is this and this. And everything is actually mapped to here. And we have another one here. So the other end is somehow this one and this one. And I have a blue disk attached to here. And everything here is actually mapped to here. But this disk is mapped to here. Right? So somehow, if we just study this sort of phenomena, and then this red, yellow, yeah, they don't really exactly cancel. Right? They don't, yeah. But anyway, so we have this contribution and this contribution. So here you have a contribution of holomorphic disk on this green side. And here holomorphic disk appear on the blue side. If these two somehow contribute to delta square in the same way, and then somehow we can just cancel them. So this is the argument which actually Yonggen noticed for the monotone Lagrangians with the Hamilton isotopic each other, and minimal mass number is at least 2. Because if these two are Hamilton isotopic, and monotone case somehow holomorphic disk here and holomorphic here, both sides actually corresponding. So I will come back to this because this I may extend for, in a sense, general case. So this is just I want to remind you.
When n is equal to c, they're already cancelled. When n is equal to c,
yes,
they're already cancelled.
Yes. So this cancels. That cancels. No. I said this cancels. That's okay. By computation, it cancels because this y equal to 0. But I just want to compare these things. So this case, actually, it is not 0, right? I look at some component of the moduli space. And then I just look at one component moduli space and look at its ends. And if no bubbling happens, then just this consideration is enough to show delta square equal to 0. And how about this case? In this case, you have one, yes. So this one doesn't work. So look at look at the, yes. Okay, so what we want to say is the following. So if you consider the moduli space of holomorphic strips of index 2, and then want to show that whose boundary somehow contribute to this. And then it is 0. But there are some ends which doesn't contribute to delta square. So such thing must some compensate with other effect. So this says that if something happens one side and a similar thing happens the other side, these two effects can cancel. So therefore, so this is, maybe I may keep saying this more. Okay, so anyway, this is just one thing which I want to say now. Because in this case, you can compute it, so therefore you can do it, right? But if you don't know exactly what delta is, but still you have this sort of contribution. I mean, if you have some contribution from one side of the boundary and the other side boundaries, you can compare these two effects. Then sometimes you can actually show that delta square is equal to 0. So, wait. So maybe I just want to make experiment. So, for instance, yeah, just remember what he did last time. Yeah? So here you have x omega, and then take L inside x. It's a monotone Lagrangian, and the minimal Maslow number is at least 2. In fact, if it is bigger than 3, then general story works. But in this situation, and then if you consider L0 is just L, but L1 is actually a phi of H of 1 of L, right? So just Hamilton deformation of it. And then you can define the CF L1, L0, and usual counting of holomorphic strips. Then delta square is equal to 0. So exactly he had a chain complex. And how he can show this? So what he proved is somehow you have something on one side, then you also have something on the other side. So these two effects cancels. I just want to explain such a thing by example.
Okay, so you mean when A equal to C, these two cancel?
These two cancels, yes. Sorry. If A is not equal to C, then the areas are different, so therefore it do not cancel. Yes. Okay, so maybe now Okay, so this is the story. And so first I want to discuss certain obstruction classes. Okay, so let L be a Lagrangian submanifold, maybe closed embedded Lagrangian submanifold. And in fact, in general situation, I assume that this has a spin structure. So equipped with more precisely, more generally, we have a notion so-called relative spin structure, but today I just use ordinary spin structure. So let's consider L, closed embedded Lagrangian submanifold equipped with spin structure. And then from here, I want to define certain obstruction cycles for defining Floer complex. What does it mean? So maybe I just explain our terminology, this obstruction cycles. So as this name suggests, if all the obstruction cycle vanishes, then we can actually find a way to define Floer complex. That is obstruction cycles. But what does it mean? This. So for instance, if you have a say certain fiber bundle here, fiber bundle over say CW complex, and then you want to find some cross section of this fiber bundle, and then first you just take a zero simplex, and then take its inverse image. And then this is a section over the zero skeleton. Next, you just take one simplex, or maybe one cell, and then ask whether you can extend the section over zero skeleton to the one skeleton, or one cell. If you can do it, and next you try to consider two cells, and then try to extend it to the next cell, right? So you can define some obstruction classes inductively. So first you start with zero cell, and then if it is, you just pick one choice, and then you proceed to the one cell, and then you ask whether you can lift it or not, and then it is a first obstruction. If it is 0, and then certainly you can proceed to the next level, and then you get obstruction for the two cells over 2 cells, and then if it is 0, you can proceed to the third, and so on, right? So here, some similar flavor. Certainly not really this. Okay. So first I consider the following things. Let's consider beta. It's a second relative cohomology class, somehow represented by holomorphic disks. So I consider all beta maybe represented by J holomorphic disk, right? And then maybe I denote by G0. And then next I consider G, which is actually a monoid generated by this G0. Okay? So this is monoid inside of this. Just you allow addition. Okay? And then by so-called Gromov compactness, so you actually this G is actually written the following. So first one is actually trivial class, and then you have beta 1, beta 2, and so on. Certainly you can enumerate them with the following property. So if you take the integral of omega over beta I, then this is less than or equal to the integration of omega over beta I plus 1. So the simplex area is weakly increasing and diverges to infinity if, just this condition. So take this G as a monoid generated by G0, and then you can order them so that satisfying this property. If it is empty, certainly we don't have anything. So therefore, in that case, actually, no problem, because if you don't have a holomorphic disk, then you don't need to worry about anything. Certainly, you may ask whether you also need to consider J-holomorphic sphere. And certainly, you can also include it. But in fact, by using virtual techniques, certainly, somehow this J-holomorphic sphere is not really a main issue here. But so in a sense, actually, we can actually only consider holomorphic disk classes. So anyway, so this is one. And next, I consider this M beta. So M beta is a moduli of J-holomorphic disks representing class this beta. So it's roughly speaking, you have this Q and J holomorphic, so that this class is equal to beta, and then you just mod out by the automorphism of the disk. So this is PSL to R. But sometimes I also want to consider some marked point on the boundary. So here I may just write maybe K plus 1 here. And then here I consider Z0, Z1, Zk on the boundary. So they are actually distinct. So I just take a distinct boundary point and respecting the cyclic order. The boundary orientation. This, right? So basically, I have some disk here, and then I have Z0 here, and then Z1 is here, and Z2 is here, Zk is somewhere. And Z0, Z1, Zk can move, but it has to be put in respect to this cyclic order. And then I have a map to this. And so this is the homological map. And then, model out by this. So this is a moduli of J holomorphic disks representing class beta. And now I need some compactification of this. So maybe better to denote it by this with circle. And then now I consider M, K plus 1 beta. So this is a moduli of bordered stable maps of genus 0 and connected boundary and K plus 1 boundary map point. So namely now the domain need not be just one disk. Maybe domain could be some tree-like configuration of disks. I don't know, maybe many kind of things can happen. And even or maybe on some component you may also have this sphere. Many sphere may be attached here. I don't know. So this kind of stuff. So union of disk and sphere, and the sphere actually attached to an interior point of the disk, not on the boundary point.
But in this definition of K plus 1, where does Zi go under U? Or there isn't any?
No, this one, right? Yeah. Z0, Zk are just domain, on the domain.
Yeah. But what do they do under U?
U is just a mapping from disk to here, disk to Excel. And Z1, Zk as the point on the domain. So,
right. So, but why this is abstract information?
I will tell you. And anyway, so in this case, if you look at the boundary of this, I just look at the boundary of this, the boundary is here, and boundary here, right? And boundary here, boundary here, boundary here. What I'm saying is, this boundary is actually connected. Just like this. So connected boundary, and then I may have a bunch of mark points on it. I don't know. Some component may have, some component may not have, but anyway, so I have a bunch of mark points. And then if I start from Z0, then still we can talk about a cyclic ordering, because these disks are kind of tree-like configuration. So therefore, you can actually give the cyclic order of this. Okay, so this is one I want to say. And so marked points are points on the boundary in this case, mutually distinct, and also, so they are mutually disjoint. And away from boundary node. So boundary nodes means these intersection points of disks. These we call boundary node. Okay? And these points are called interior nodes. So anyway, so this is a domain. And what is a stable map? So I denote by this sigma. So then sigma, d sigma map to this XL. And so sigma may consist of several connected components like sigma I. And so our map U here is actually continuous first. It's a continuous map. And if you restrict a U to each component sigma, and then you have a user J-holomorphic map. J-holomorphic disk in this case. So each component is either sphere or disk. And if it's a sphere, it is J-holomorphic sphere, disk, then J-holomorphic disk, and so on. And what else? Yes. So this is actually a holomorphic object, so that it's a bunch of holomorphic disks, maybe holomorphic spheres, so that these nodes actually map to the same. Yeah. So nodes belong to two components, and so therefore the map is defined on both components, but maps coincide at this node. Yeah. So this is just a continuity. And then the stability condition. Stability condition is actually the finiteness of the automorphism group. So this is U. So this one is finite. So what do you mean? What do I mean by automorphism, right? So I have sigma here, and then d sigma here, and z here, right? So this z vector is just a bunch of mark points, collection of mark points, right? And then consider automorphism of the domain, so phi. So phi is a continuous holomorphic map, so continuous and holomorphic on biholomorphic, sorry. Continuous and biholomorphic on each component sigma I, and phi of zi is equal to zi. So these points are preserved by this. And then I have a map U here to XL. And then I have a map here again U. If this one commutes, then we call such an automorphism phi automorphism of this mapping. So it's not the automorphism of the domain curve, but automorphism group of the domain curve preserving mapping U. Okay? So this is the stability condition. Okay. So we require such condition for this map U, and then just consider all the such stable maps representing class beta, then I get certain modular space.
So you define the X-circle in the problem, instead of considering stability condition, you directly wrote out by the automorphism group. So is it really the open part of the?
No. Not necessarily. Actually, if you have this, then you may think of it as a kind of open part, not necessarily, yeah. So actually this one certainly contained here.
But on the above, you wrote out by the.
No, this one, this condition is not really this condition, yes. So here, the equivalent, you consider two things, right? Sigma, d sigma, and z vector here going to XL, right? And then here you have sigma prime and d sigma prime and z prime going to XL, right? U and U prime. When do you identify them? So we identify them if you have a mapping from here to here, and yes. So this is actually the same thing. So if you have some psi which actually sending this one to this one. And then, okay. So here actually I don't really preserve any point here. I mean, because so I have disk here, right? Sorry. I have disk here, right? And then I have, say, certain 3 point here, right? And then I have disk here. I have this 3 point here. And then you have a map here which sends this point to this point. Right? And then I have a map, say, here U to Excel. Right? And then we have a map like this. Right? So somehow this U and this U, this thing and this thing both belong to here, right? And we identify them. So in this case, I don't really consider phi preserving these points on the domain. These domain actually move to other points. Right? So here, I just consider this map and then model by this. So actually, yeah, the action is somehow, yes. So in this case, actually you have D and DD and say Z. Okay. Okay. I think it's already clear enough. So maybe it's not really necessary. But maybe maybe I can just say this. So D, Z1, Z0, Z1, ZK here, right? And here you have another one, D, DD, Z0 prime, Z1 prime, ZK prime, right? And you have a map U, right? And then you take automorphism from this thing. Or maybe just an automorphism disk. Boundary should be preserved. And then how we consider the action of this on this, right? And so this one is equal to the mapping from here to Excel. And this one may be U composed with, if it is a left action, maybe I take this phi inverse. Right? And then here actually Zi prime, this may be phi of Zi. So these points of change and these actually, does it make sense? So here I consider the action of this guy, that certainly the automorphism on the domain acts on the space of maps, just composing from the right. And then map points also map to this. So therefore so when I model by this, I don't really consider the automorphism preserving this. I just move to other point. And this is a stability condition. This is a condition. So this is a definition for this action, right? And you can consider this definition action for this kind of stuff. But stability is somehow, condition. One is definition, the other is condition. Okay. So I have this. And then I want to tell you, the following. So people may call this MK plus 1 beta. sometimes people may call it a stable map, or maybe bordered stable map compactification of this one. But this is not literally true, as you said. So even this one is empty, there may be something. So this terminology is not really nice. So sometimes there are some cases. There are cases where this is empty, but this mk plus 1 beta is non-empty. So therefore it is not a compactification of this thing. Maybe I may, if I have time, so this is also for usual stable map moduli space. So this is just a terminology. So sometimes we may call this one the stable map compactification, but in fact we define this. No, I already erased. I defined moduli space mk plus beta by this thing. Okay. So but anyway, I just start discussing this obstruction classes. Okay. So now first I consider beta 1. So beta 1 is the class with smallest area among those represented by holomorphic disks. So therefore, if you consider this M beta, this one is already, if I take this one is already compact, right? So without boundary. Because beta 1 has the least area among those represented by holomorphic disks. So therefore, no bubbling happens. So therefore, no holomorphic disk bubbles. You may have, certainly, if you care about the spheres, then certainly you can also include the sphere class. But as I said, somehow, if you consider the boundary of the moduli space, and then actually sphere is not really a matter. So anyway, so first you consider this. So this one has no bubbling phenomena. So it's a compact space. So therefore, this one gives you a nice space. So sometimes you can just make it a manifold by picking suitable J, because in this case it is so-called somewhere injective curves, because simple class. So therefore it's a kind of manifold, and so therefore we have M circle 1 of beta 1. So this, I put one mark point on the domain on the boundary. So I have a disk and then put one mark point on the boundary. And boundary is actually a circle. It's also compact. So therefore, this is also a cycle. It's a cycle. So therefore, if you take mapping here, so this is a mapping from D, and then I have one map point Z0, and then I have a map U, right? So I have a disk and boundary map point Z0 and mapping U, and then I can map it to U of Z0. So this is somehow answering your question. So putting mark point, you can talk about the value there. So we call it actually aberration map. So you have a cycle, and then you have image of the cycle. So therefore, this one gives you a cycle, right? Maybe I just move to this side. So maybe I just write O1. O1 is actually this F0, M1, beta 1, 2, L. This one. I can put circle here, or maybe without circle, because anyway, in this case, it's the least class, so therefore you don't have so many, only one component, right? You have only one component, so therefore either you put circle or not, doesn't really matter. Okay, maybe I just write it in this way, but this one is in this case actually M1, beta 1. So this is the first class. So it's a cycle in L. Okay. So as I said before, in the obstruction theory, for the existence of sections of fiber bundle, we define obstruction classes inductively, and if it vanishes, you can proceed the next stage. So here we also consider same thing. So let's suppose that O1, OK are defined. So that corresponds to these classes. Are defined. Suppose that these classes are defined and all of them are null homologous. So like Oj is equal to the boundary of this Bj. Yeah, so maybe I may put some minus sign here for some reason, but anyway, it doesn't matter. So J from 1 to K. Okay. Then we define the next obstruction class OK plus 1 as follows. Okay. So maybe I just write something first and then explain what it is. So we consider this M K plus 1 of, sorry, this is K plus 1. Okay, so maybe better to use another one. Maybe I use, I don't know, maybe P and P plus 1. And here P. Okay. So I discuss the following thing. So I may consider this thing B, and then BI1, BIK. Okay. So this is just a notation which I will explain right now. And here, beta is a class represented by holomorphic disks. And this B, I1, BIK, one of this, yeah? So they are one of this B1, BP, okay? So what it is? So this is the following. So here, it is a map. Sorry. Maybe I already used maybe stable map. So I have map K plus 1 map point on the boundary of domain curve, and then I have a holomorphic map U to XL, right? So that this U is a border stable map. And still we can talk about the class represented by U is equal to given beta, so that these map points Z1 to Zk are mapped to one of them. So U of Zj is belonging to this B of Ij. Okay. And then maybe by just mod out by the equivalence relation among border stable maps. So from now on, maybe I may just write this way. So mk plus 1 of beta. So this is the moduli space of border stable maps of genus 0 and connect boundary and k plus 1 map points on the boundary and representing class beta. And then here I have B I1, B, IK. So these are just chains. Yeah? There are certain chains in L. So we can just include it because it's a chain. You can think of it as a subset or sub. Yeah, it's a chain in L, right? You just naturally include on here. And here actually I have a evaluation map at first mark points, then evaluation map at case mark point. So I have points Z1 to Zk, and then take a value of U at first mark point to the case mark point, and require that they meet with this. So that condition exactly this, right? So later I may just denote this kind of stuff by fiber product notation. But anyway, so this is a mk plus 1 beta I bi1 to bik. So what does it mean? So here I have a say disk, and then I have a bunch of map points like a z1, z2, zk here. So many map points maybe map to x and L. So I have a bunch of marked points, and these marked points are mapped to something like this. So they are actually, here are some chains. Here are some chains like bi1, bi2, and bik. And so these points, z1, z2, zk, are actually mapped to those bi1 to bi2 and bik. So this is the kind of object we consider. And finally, I consider the next one. So this is just a notation at this moment. So maybe M1 sharp beta. So maybe this is rather strange notation, but anyway, this one is actually a union of the following things. Union of the following things. Here I have a beta I, and then beta I1 plus beta IK is equal to beta J. Sorry. I'm talking about beta P plus 1. Sorry. Okay, so I have already defined this O1 to OP and then try to define OP plus 1. For this, somehow we want to consider something like this, but not exactly M of beta P plus 1. So this is kind of extended object, and here it is. So does it make sense? So I consider this beta P plus 1 because I want to consider this one. So somehow I want to consider M1 of this beta P plus 1 somehow. But because this class is no longer the class of least area, so therefore there may happen some bubblings. If you have bubbling, actually it contributes to the boundary. So therefore we have to understand how the boundary appears, and then this one is not a cycle because you have a codominant one boundary. But nevertheless, you can find other pieces so that if you glue them together, you get a cycle. So originally this one is not a cycle, but I just add other kind of pieces, and so in the end this becomes a cycle. So I will explain it a little bit more later. But anyway, so here, now I have another one. So because here I have a map again to this. Okay? Because I used Z1 to Zk to put these constraints. But Z0, the first map point, the zeroth map point, was not used in this definition. So therefore, still I have one remaining point, and then take value of u at this remaining point. Okay? So because this one is a cycle, this one is a cycle, and so this one gives you, yes. Okay, so this one, okay. So therefore, the definition of the OP plus 1 is actually this one. Okay, so this is the definition. So I started from O1, so this is actually okay. It's okay. And then let's suppose that O1 is a boundary of something, then I can use this information to proceed to define O2. And then if O1, O2 are defined and O1, O2 boundary of something, then using this, actually I can proceed to define O3. If O1, O2, O3 are defined, and all of them are null homologous, then picking these things, and then we can define O4 and so on. So this is actually inductive way to define this. And why? No, these are actually anything. These are anything. I want to ik, maybe 1 to p, any 1 to p. No, consider all possible things. All possible things, because I take a union here, all possible things. Sorry, I have to also write it. So I1 ik, so this is a union of all I1 to ik. And so that the only constraint is that they correspond to the class G, beta I1 to beta ik. So then consider this beta I, and class is beta I1 to beta ik. If you sum them up, then you get this class. So this is the only constraint. This is the only condition. You consider all possible such things. And then eventually you get a cycle. And then you can proceed to the next stage. And if it is trivial, this is again null homologous, then you can go further. So what is this?
Part of the dimension of the modular space.
Okay.
Yeah, potentially am I wrong?
Okay. Maybe it's also a good point. So therefore, I may also do this. So maybe I can tell you the yes. So you have this m, k plus 1 beta, and then take that so-called expected dimension by the index theory, and this one is equal to n plus mu beta plus k plus 1 minus 3. So this is a formula for disk. This is a formula for disk, and the same formula is true for this.
So without k, this dimension could be negative. Is that right?
Yeah, but then in such a case, it may be empty already. Because geometrically it's just a point on the domain.
So your reason to put in k is not to make the dimension positive, or is it?
No. That is not the way. So actually, so last time I discussed other things, like varying almost complex structure or so on, in order to define the chain homomorphism or maybe chain homotopy. In such a case, I introduce such a variation of J and so on, then actually the dimension of the modular space for this extended one really increases. So therefore, even though just the index difference is -1, the modular space for chain homomorphism is actually zero dimensional, right? So in that case, actually, it is really something contributing the dimension. But this one is just information on the domain. So this is the expected dimension. Maybe I should also tell you. No. Last time I already did it somehow. So therefore, maybe it's okay. So this is a modular space for this, right? Z0, Z1, Zk, and going to this, right? Yes. So this is the open part of this, in a sense. And if you have like this. Like this. And then the dimension of this guy is actually less than this by 1. So you have this node, and then the dimension decreases by 1. In fact, here you have automorphism, PSL2R, this is 3-dimensional automorphism. And here you have a 2-dimensional automorphism because this node point is a special point. So therefore, I keep this point, so therefore, here the automorphism is 2-dimensional. And this is 2-dimensional, so add them up to 4. This is 3, here 4. So therefore, if you mod out them, actually you get the space of dimension 1, the dimension of this guy is equal to the dimension of this guy plus 1. So this is, in a sense, this is the codimension 1 strata. So if you have this and this, so this is actually codimension 1 strata. So you consider all possible way to split into 2 components. Then actually this is like a codimension 1 strata. If you have 3 components, actually it is a codimension 2. So it's a codimension 2 corner and so on. So anyway, so this is the formula. Okay, so this is automorphism. Okay. So maybe it's maybe not so easy to explain the complicated case. So therefore, I just consider one special case. So why this becomes a cycle? So this is the following reason. So let's suppose that in this picture, like, so I have beta here, and then I have a moduli space of stable, maybe just a holomorphic disk class beta, and then maybe I put one map point here. And then one of the boundary, so it contains certain boundary of this, right? And then some component, the part of the boundary. Part of the boundary of this M1 beta, yeah, contains this. Sorry, M2 beta and M1 beta, something like overlap, right? So this one is this one, so represent class beta. And then it may have, it may split into this way, and then that is this one. Okay? So this one, I have following picture, right? So this is actually beta prime disk, and this is beta double prime disk, and then here I have a Z0 here, and this is a node like this. And how to understand this? So this is a fiber product. That means you have beta prime disk, Z0, and then here I consider the first or second map point of the disk. So I just forget this part. Then I get this part. And then here I consider modular space like M1 beta double prime. Okay? This one. And then consider the evaluation map to L, right? Okay. So this one is some modular space, and then because I have one map point, I take an evaluation map from there. And this one is exactly the pair of beta prime disk and the element here, so that the image of this element by evaluation map actually coincide with the evaluation at point Z, right? So namely, I have something here. So I have this modular space, and then this modular space may be something like this, right? Image of this modular space may be like this. And then if they intersect here, then you look at the inverse image of it. The inverse image of it is nothing but the stable map, right? So therefore you have some map. So therefore it meets here. That means you have another disk in class beta double prime, so that they meet this node point, right? So you understand this. So now I consider it as a boundary of other moduli space. So this is boundary of M2 beta prime and this B double prime or something like this. So B double prime is yes, as above. So somehow this boundary is equal to this M1. Sorry, M. So this is not really, I mean, precise. But if I put here sharp, and then this one, yeah, so I assume that this is a cycle inductively. So if I take here sharp here, and I take sharp here, so this picture is just without sharp. But I want to show that this one is a cycle somehow inductively. And then at the beginning it is really a cycle because without sharp actually it is already a cycle. So therefore we start from the cycle. And then just consider this. And then if you look at this, it's a cycle. And then cycle is a boundary of something here. Right? So now what I'm saying is the following. So so now I have this sharp here, right? And then it's a cycle, so therefore you may have some cycle like this. Yeah? I don't know, some cycle here. But if you have another one which bounds this cycle, right? So it bounds this cycle. Okay, yellow one is okay. So let's suppose that you have this something like this. And then you can consider this modular space. And then take its boundary. Then you also find this as a boundary of these things. Okay? Because here you have beta prime disk. And here I have some yellow one here, right? I consider beta prime holomorphic disk meeting with this yellow B double prime. And then part of the boundary of such configuration is actually beta prime holomorphic disk meeting with the boundary, right? So you consider the condition that this disk meet with some point on this chain. And then look at the boundary of this. One possible boundary is actually boundary of this one. That is another kind of bubbling. Another type of boundary is the fiber product of this guy with the boundary of this guy. And that is nothing but this. But this one is nothing but this thing, right? But this one is equal to F0 of this M1 sharp of beta double prime going to L. So therefore, you can find the same thing. I mean, at the beginning, if you look at the boundary of this, you have a bubbling of phenomena. You may have bubbling of phenomena. So therefore, you may have this sort of fiber product of two modular spaces. But if this one is a boundary of something, then you can regard this as also a boundary of some other modular space. So therefore, if you group this one with this one along this codimension one strata, and then at least you can cancel this part of the boundary. So like you have here, you have some modular space like this. So you have a modular space like this. And then you may find some other piece like this, so that somehow you can cancel this effect. And then you may also have another one like this. And then you can kill part of the boundary. And then you can keep doing it. So therefore I need to take all the possible unions. Is it clear? So here actually this is just kind of one bubbling phenomena. And then I try to find another piece like this. And then this part of the boundary is actually cancelled with the boundary of this new guy. If you have this, and then you also try to find another one. And here the corner, actually it is actually 3 component things. But then you can use these 2 things, right? I have this B, carry B for this guy and carry B for this guy. I use 2 things. And then you may find another piece. And so in the end, somehow you can find something like this. So therefore all the boundaries are cancelled out. And then you get a cycle. And then you can proceed to the next level. So this is our original motivation or original way to understand this observation classes.
What set are these abstractions? What set are these abstractions for? They are abstractions for doing something.
Actually, this is observation for defining Floer theory. I will explain it next. So I have this L0 and L1, two Lagrangian submanifold. Okay? And then for L0, maybe I have observation classes. O1 of 0, OK of 0, and so on. And also O1 of 1, OK of 1, so on, right? So just consider this construction of both sides. And let's suppose that this OI are just boundary of something. And this OI is also boundary of something. Let's suppose you have this. Let's suppose both sides you have this. And then we can use this use these things. We can use these things, B0 and B1. So that delta of B0, B1 square is equal to 0. So what I said is somehow the following. So we can define this OK inductively. Let's suppose that you can define all the observation classes and also all of them are null homologous. And then pick those data for both sides of the Lagrangian manifold, I mean L0 and L1. And then using this data, somehow you can rectify the boundary operator of the Floer differential so that this is really a boundary operator. So maybe this Floer's original differential, right? This CF to CF. Consider just a holomorphic strip mapped to this, right? It's a holomorphic strip. So we consider such a thing. And then count number of them define this. Yeah. So therefore, so delta P is equal to sum of the number of this M of PQ and Q. maybe I need to put a tilde there, but somehow we consider it's this. So this was 1. Yeah? But delta square may not be 0. So, but this actually caused by holomorphic disk bubble. Right? So that is actually, so you have these things like a P, Q, and R or something, and so like this. And then if you glue them together, you have something Q and P. But then in the end, you may have this sort of things, right? And then, because of this, actually, we may not be able to delta square is equal to 0. Right? So now, I consider something similar to this. I mean, here I consider I consider this modular space. This modular space. This one is the modular space of holomorphic disks meeting this curly B. And this curly B is a boundary of this kind of stuff. So now we also consider something similar. So let's suppose that this holomorphic disk is in class beta. Okay? Then we consider the other modular space of the following form. So here I have a boundary mark point which meet with this. So this one actually, sorry. Maybe better to use the previous notation because otherwise it may be a bit difficult. So maybe it is beta j, and then I consider some cycle like a bj. So namely, it's a holomorphic strip with one mark point on the boundary. And this mark point is actually mapped to this cycle, the chain Bj. Okay? And then what happens? So I consider this modular space. So now I consider the following modular space. Okay. This maybe I just because story is very similar to this, so therefore I want to keep it. Okay, so now I consider this M, P, Q, and this B, J or something. Okay? So what it is? So this is actually a W from R cross L1 to XL, right? XL 0L1, it's a J holomorphic strip, right? So that I have a one mark point on the boundary, so W of tau 1 of 1, right? Say, lying in this Bj, for instance. And tau 1 is also a data here. But then modeled by translation. So in this case, actually, it doesn't matter whether you take this tau 1 here and then model by translation, or you put this one condition W01 belongs to this without translation. But anyway, so in general, maybe better to keep it. And then if you take the boundary of this, so it may be several possibilities. So one possibility is actually this M, P, R, M, R, Q, and Bj. This may be one possibility, or maybe M, P, R, Bj, and M, Q, M, R, Q. this is also another possibility. So maybe the modular space of strip actually split into pieces, and this constraint may be satisfied the first component or second component. And another one is actually this M, P, Q of boundary of this P. So we have these three components. And here it's a modular space of strips. And then if you take its boundary, it has some components. So one of the components is certain M, P, R, M, R, Q. But another component is this sort of stuff. So therefore this is M, P, Q, but some bubbling holomorphic disk, right? So therefore I put one mark point on here and then take a fiber product over L1 of this M, beta, J, 1, right? This thing. Maybe we also have another one like M, 1, PQ, and L0 and M1, beta I or something. This one is for L1 and this one is for L0. So anyway, many cases. But anyway, so this one may have this boundary. If you have this kind of boundary, you can understand it as a fiber product of this modular space from P to Q and this evaluation map of the holomorphic disk in class beta J. And now I consider this modular space too. So this modular space is a holomorphic strip from P to Q and meeting this curly Bj. And this one has also several components. But if you look at this one is same as the evaluation 0 of this M1 beta double prime, beta J to A1, right? So therefore, this contribution and this contribution actually cancels. So in the holomorphic disk, modular space of holomorphic disks, I consider all possible ways, the bubbling phenomena, and then look at, according to this, you try to find another piece to compensate the boundary. And here, if you have this sort of things, then we consider this, and then this thing actually cancels with that. Namely, gluing this moduli with this moduli, this part of the boundary actually cancel out. So therefore, what we do is the following. I don't know this is how much it is appealing, but so now I consider following modular space. So now more precisely, I consider this M, P, Q, but I put mark point K0 mark point on the lower boundary and K1 mark point on the upper boundary. So here I have here, and maybe K0 point, I don't know, maybe here I have a Z1, sorry, here maybe, here I take Z1 of 0, Z0 of K1 here. And maybe for some reason I just start from here, Z1 of 0, G1 of 1 to Z1 of K1. Okay? So I put arbitrary number of mark points on the boundary of this strip. And then consider the, yes, so here this one is R cross 0, 1. And then we have also this mark points like Z0 vector and Z1 vector going to the mapping to X L0, L1. So lower boundary is mapped to L0 and upper boundary mapped to L1. And we have a certain limit condition, limit tau tends to plus minus infinity, So let's denote by W, and then W of tau t is equal to P, and limit of tau plus infinity of W tau t is equal to Q. And then finally I assume that this W of this Z I 1 0 is mapped to some chain like B. Sorry, maybe better to use J. Sorry, B0 J. No, IJ. Sorry. B0 IJ. And W of Z1 J is in B1 IJ. And then equivalence relation. So I want to consider such a moduli space. So maybe I need to put more space here. So this is M and K0, K1, PQ. And then here I have B0, I1, B0, IK0, and B1, I1, B1, IK1. Okay. So this is actually very similar to the modular space I wrote before, mk plus 1 or beta and bi1, that's the bik. So I wrote this for just one Lagrangian. But here I have two Lagrangians. So therefore I need a two set of these curly B's, K0 many or K1 many of them, and then require the constraint at these boundary mark points. And so this is the modular space we use to define the boundary operator. So somehow we also include this effect. So not only this, but consider all possible things. And then actually all the boundary can cancel out. The only remaining boundary is actually kind of splitting things, splitting of this type. So maybe I split. So maybe I have this. So these mark points are mapped to some B, curly B's, and then it may split into two things like this. So these mark points are mapped to curly B, and then as a strip, it split into two strips, gradient trajectories of the Floer action function now, and then these constraints also put in one side, either this side or this side. So then if you look at this object or this object, it also belongs to similar modular space. So somehow what we consider is the following. So how we define this? So in this case, actually what we do is somehow, again, we consider M sharp of PQ. It's the union of this M, P, Q, and all possible BI1, BIK0, and B1, I1, B1, IK1. You consider all the possible unions, and then using this modular space, maybe you can define delta P is equal to the sum of this modular space and this. And so here I use this B0 and B1, and then we can show that this one satisfying this. Okay. So I don't know whether this is how much it is appealing, but this is somehow geometric picture of the rectifying the boundary Floer's boundary operator. Okay. So up to now, actually, what I said is just, I mean, I don't know how much it is actually good, but maybe you may think that, yeah, maybe you can understand part of it, but how to really see the dependence of this boundary operator on these chains. And if we have a boundary operator, certainly you can talk about cohomology of this, and how the cohomology depends on these choices. Right? And so somehow in the afternoon, maybe I just start from filtered infinity algebra and filtered infinity bimodule picture, and then I can just reformulate all this sort of stuff in that terminology. So here actually I'm a little bit vague, but somehow idea is always starting from the moduli space of a certain object and look at the boundary, and then what happens, and then from here actually if you want to have some other things, then you try to cook up some other moduli space and do this. So what we are doing is, maybe I just stop now, but in the afternoon what I want to do is the following. So first we may have a geometric input, like a moduli of, say, holomorphic disks. Maybe this is a maybe kind of solution space of certain geometric PDE. And then somehow we want to consider suitable compactification of it. It is not really a compactification of this one, as I told you before, but it's just a kind of slogan. So here I take certain suitable compactification. So not really true. Terminology is not really true. But anyway, so consider this and then try to consider some suitable extended object. And from here, we want to cook up some algebra. So, for instance, holomorphic disk or holomorphic spheres, holomorphic objects, maybe holomorphic objects. So example first is actually you consider moduli of say holomorphic spheres, or these rational curves, or maybe just holomorphic curves. And then here we consider the moduli of stable maps in the sense of Kontsevich. And then from here you get a bunch of things. Maybe you may have a quantum cohomology, or maybe Gromfit invariant. And Gromfit invariant satisfies certain axioms, right? So actually, yeah, so this sort of story. And if we have a moduli of a holomorphic disk, then here the moduli of border stable maps. And then from here, after we will cook up this filtered infinity algebra. And if you consider moduli of this strip, then again we consider the stable strips. Then from here, actually we can cook up filtered infinity bimodule. Or maybe you have a polygon, holomorphic polygon, and then you also consider stable one, and then you get so-called these Fukaya category structures. So somehow, so this sort of things. So originally, yeah, I don't know, maybe this holomorphic sphere case, maybe you know quite well. And then quite important thing is the moduli of the domain curves. So if we have this moduli space of genus G, K map points, stable maps, representing class A, say, and then you have a forgetful map, MGK. So certainly in some cases you don't have this forgetful map. You just remember, yeah, no, so it's a kind of information of the domain curve. And also you have bunch of evaluation maps, right? And for instance, in the case of quantum cohomology, certain quantum cohomology basically use P1 with 3 map points, and then you require that this sphere intersects with 2 cycles, two cycles in X, and then take evaluation of this remaining map points, and this gives you some sort of binary operation, and this binary operation is associative, so that it becomes algebra because you can consider the following thing. Like here you have maybe just 4 points, 1, 2, 3, 4, 1, 2, maybe 0, 1, 2, 3, and then you have 2 different degeneration of this. Sorry, maybe not so good. You have so maybe here I have 0 here, and then here I have 2 here, and here I have 3 and 1 and 3. Or maybe you have here 0 here, and 1 here, and then here you have 2 and 3. Maybe this is not so good. I should write different order. Maybe this may be better. So I have 3 and 2, 1, 2, and then 3. And yeah, maybe this is better. Yeah, like this. So you have a 4 points on P1, and then so you consider this is M04, and this is actually isomorphic to P1, and then these two are 2 degeneration of this guy. I mean 2 special points of this, and so if you look at this and consider this evaluation so on, so here I take a product, first, second entry, and then third entry. And this one is first take a second entry, third entry, and then multiply with first one. So therefore, in this space, actually, we have a path, and this path gives us certain cobordism moduli space. So therefore, we can compare these two. So in this case, what I want to say is, I don't really want to say so much about this, but in this case, we can work with cycle levels. So starting with cycle, end up with cycle. So therefore, everything close in cycle level. Therefore, you can actually easily work on homology level. So you take a representatives, and then resulting thing is also in well-defined homology class. That's okay. So because spheres or maybe closed curves, no codimension 1 bubbling, no codimension 1 degeneration. Therefore, we can work with cycles. So these actually we can work with cycles. But once you have boundary, then you may have a boundary bubblings. That is codimension 1. So therefore, in this case, we cannot really work with cycles, because even though you start with cycles, you may end up with some chain which is not cycle. So therefore, at the beginning, somehow we have to deal with all the chains. So this is actually, in a sense, cycle level construction, but this one is chain level construction. So that is a difference between this and this. But both of them somehow rely heavily on the moduli of the domain curve. So maybe I just start from here and then explain something about this. So this is just a motivation. This morning talk is actually motivation for filtered infinity algebra. Okay, thank you very much.
Does the inclusion of Zi and Bi change the action function now?
So for this one,
The action function, does it change?
actually that is true. So okay. So maybe I should be. Okay. So this is just a answer to you, and maybe other people may not be. So for this, actually, I have this mk plus 1 of, no, sorry, when I consider this m1 sharp of beta, I wrote that this one is actually union of something like a beta I and bi1, bik, and here beta I plus beta I1 plus beta ik is equal to this beta of something. So I define something like this. So here actually I always somehow gives you some homology class or homotopy class. And now I consider this MPQ, the modular space of strips. I also have to put such information. So in fact here I need to put some information here. No. So like this. So last time actually I always wrote this M, P tilde and Q tilde so that I can keep this. So today actually I was a little bit lazy to do this. But so if you do this, then it is one way. But here actually I can give you another way. So here I have a path space, L01, and then here you have a constant map P and constant map Q, right? Then I pick a path here, right? Path in this path space. So maybe I just denote it by this path class B. So B is a homotopy class of path from P to Q. So maybe B is a